All right, in this video, we're going to show how to derive some results involving integrals of Legendre polynomials using this integral result that we derived in the video entitled orthogonal properties of Legendre polynomials. All right, so the how this works is we compare each integral with this and determine the value of the function f, and then we simply plug this in the right hand side and evaluate. Something that is going to be of use and occur frequently in this type of calculations is this integral here of 1 minus x squared to the power n dx. So again, we have worked on this integral in that same video on the orthogonality properties of Legendre polynomials, and we have shown that it is equal to 2 to the power 2n plus 1 times n factorial squared all over 2n plus 1 factorial. So for the first integral here, we have got x to the power n pn of x. So what it means here is that f of x is equals to x to the power n, and so the nth order derivative of this is going to be the nth order derivative of x to the power n, and this is equal to n factorial. A good practice would be for you to make sure that you can prove this by mathematical induction. So prove that the derivative of x to the power n, if you differentiate that n times, you get n factorial. Okay, so if we plug into that formula now, which is this right hand side here, then our I is going to be 1 over 2 to the power n times n factorial 1 minus x squared to the power n, and then the nth order derivative of f, we've just derived it to be n factorial, and so the n factorial here in the numerator and denominator will cancel out, and so now we just have 1 over 2 to the power n times this integral here, which we mentioned earlier occurs frequently in these type of calculations. So if you just plug in that expression that we showed, then this is now a step away from showing that our integral is indeed the required integral on the right hand side. So if we cancel out the common factor of 2 to the power n, we now have 2 to the power n plus 1 times n factorial squared, all divided by 2n plus 1 factorial, which is the required expression on the right hand side. All right, and then in B we have got the integral of x pn of x, pn minus 1 of x. So here what we're going to do is we're going to let f of x be x times Pn minus 1 of x. And then Pn minus 1 of x we're going to express using the Rodriguez formula of the Legendre polynomials. We're probably going to run out of space there. So let's just do it below here. So this is going to be equal to x times 1 over 2 to the power n minus 1, n minus 1 factorial. Then the n minus first order derivative of x squared minus 1 to the power n minus 1. Then the nth order derivative of this, so we need to differentiate this n times. So we're going to take the constant out of the integral derivative. So this is going to be the nth order derivative of x times the n minus first order derivative of x squared minus 1 to the power n minus 1. Now, what we're going to do here is we're going to use Leibniz rule for the differentiating products n times. So if we let this one be v and this one be u, okay, then what's going to happen is we're going to have 1 over 2 to the power n minus 1, n minus 1 factorial. Then here we're going to have the nth order derivative of u times v, and then n times the n minus first order derivative of u times v prime, and then lots of other terms. We're going to have n plus 1 terms in total, but these first two are the ones that are going to be relevant for this calculation. Now if we look at the nth order derivative of u, so what's going to happen is we're going to have to differentiate this n times. So that's going to be the nth order derivative of the n minus first order derivative of x squared minus 1 to the power n minus 1. And then these two operators are going to give us the 2n minus first order derivative of x squared minus 1 to the power n minus 1. Now the degree of this polynomial is going to be given by this times 2. So the degree of that polynomial is 2n minus 2. The order of differentiation here is 2n minus 1. Now you're going to notice that 2n minus 1 is greater than 2n minus 2. So that means this is going to be equal to 0, because you're taking a polynomial and you're differentiating it the number of times bigger than its degree. So that means this term, first term here, is going to be equal to 0. And then now if we do the same thing for the second term, the n minus first order derivative, so this time we are going to have n minus 1 here and n minus 1 there. So then when you combine these two, so what's going to happen this time? This is going to be 2n minus 2, 2n minus 2 x squared to the power x squared minus 1 to the power n minus 1. So this time these two are going to match. The order of the differentiation is 2n minus 2. The degree of the polynomial is 2n minus 2. So, and by the same result that we stated earlier there, then that's simply going to be the factorial of the degree of the polynomial. So this is going to be 2n minus 2 factorial. So that means this term here is going to survive. And now remember v prime, remember v is x, and so v prime is 1. So that means this term here is actually going to be n times 2n minus 2 factorial. V prime is 1. So that's what we're going to substitute this time into that formula. So let's let this thing be equal to I. So what's going to happen is that I is going to be equal to 1 over 2n into the integral of so the term that's coming from so remember here there's still this term there, so there's going to be 1 over 2 to the power n minus 1, and then in the numerator we're going to have n times 2n minus 2 factorial. Then this is multiplied by 1 minus x squared to the power n. And so if we just take the constants outside the integral sign, so this times that going to be 2 to the power 2n minus 1. Then we're going to have n factorial times n minus 1 factorial. Then integral from minus 1 to 1 of 1 minus x squared to the power n, which is a standard integral that we have talked about. So we're going to have here n 2n minus 1, 2n minus 2 actually, sorry, this is 2n minus 2 factorial. So 2n minus 2 factorial 2 to the power 2n minus 1 n factorial n minus 1 factorial. This term is giving us 2 to the power 2n plus 1 n factorial squared all over 2n plus 1 factorial. Some of these terms now are going to cancel out, so let's go through that. This term is going to cancel out with one of those terms. This is going to cancel out with that, and then we're going to have a 4 in the numerator. So let's just so it's going to be 4 in the numerator, 2n minus 2 factorial. Then there's still an n factorial left there, n minus 1 factorial in the denominator, and 2n plus 1 factorial. Now this term and this term can cancel out, but there is a few terms in between. So in between 2n minus 2 and 2n plus 1, there is 2n minus 1 2n, and yeah, so it's just 2n minus 1 and 2n, or yes, and of course 2n plus 1. So when if we do this, then here we're going to remain with 2n plus 1, 2n minus 1. Okay, so in the next step, we're going to have 4n times n factorial all over n minus 1 factorial, 2n plus 1, 2n minus 1 times 2n. Then this 2n and 4n there is just going to give us 2 here. The n minus 1 factorial and n factorial there is going to give us n there. I think we are almost there. So in the numerator, we're going to have 2n. In the denominator, we're going to have 2n plus 1 times 2n minus 1. So this now simplifies to 2n over 4n squared minus 1, which is the required result. All right, thank you for watching the video. Please do make sure you subscribe at the bottom, and if you have queries, questions, this a topic you'd like us to do, you can tell us in the comments as well below, and you can share this with your friends that you know need this type of material. Thank you very much.